So, hi Tony, how are you?
Good. What about you?
Yeah, I'm doing well. All right, just a quick announcement. We will be having our quiz 2 tomorrow. So we will start the first 30 minutes of the lecture to continue with curvilinear Newtonian kinetics. And then after 10:15, I will give you 30 minutes to start your quiz. And the quiz time will start from 10:15 up to 11:15. So you can attempt your quiz in any 30 minutes between this 1 hour interval. So this is for the quiz, and I think we will have homework 5 and homework 6 will be due on tomorrow. So just like plan to submit them on time. And today we will continue with Newtonian kinetics. And it's just like I want to make sure on one thing for the problems that we solved yesterday. So for yesterday, I told you to create a free body diagram like this one, and a one that has a kinetic diagram. And on the kinetic diagram, you construct the x and y axis and assume a direction of the motion. So here we assume that the body is moving in the negative x-axis, so MA should be a negative. And when we solve, when we use the 20-meter distance along with the time to calculate the acceleration, we also calculate the acceleration based on these direction. Like this is the x-axis and this is the y-axis. So we know that the body is going 20 meter in the negative x-axis. So we put negative 20. That's why the acceleration will be the sign of the acceleration will be corresponding to x-axis. That's why we got negative 6.009 meter per second square, which mean that the magnitude of the acceleration is 6 and the direction is in the negative x-axis. So this is how we got it. And when we used this value into the summation of fx equal max, I should like here put negative. But this might confuse you, like you got ax from here is negative, and when you have negative here, you say it will be positive, but it's not. Because here here's the direction is included into the magnitude. So in this one, you should know that the ax should be negative because you have this one. So you either keep it positive and add the negative value that you calculated here, or you already know that the 6 is the magnitude and the negative is the direction. So we put here the magnitude of ax is 6, and we know that the direction is negative, so you put negative outside. So just like make sure that you don't mess up with the signs, like you do some analysis with a negative direction and another one with positive one. So just make sure that you have your directions, the signs of your directions right. Does anybody have any questions on this? So we also like here in this one, we assume that the x and y axes, this one, and in this direction, and we have the motion in the negative direction, MA. So we should, from first, when we are constructing the Newton's second law in the y direction, we should have negative MAY. So we know AY here is the magnitude of the acceleration, and the negative is the direction of the acceleration. If you make an assumption like, what if you said that you know that the body is sitting at rest from here, so it will go down. What if you assume that the acceleration is in the other direction? So no problem. So you will have here, this one will be positive. And finally, when we solve this problem, you will find that the AY will be negative, which means it's an opposite direction from the one that you assume. So you might do this or whatever you want. So if this is much more easier for you to assume that the direction of the motion is in the positive direction with the axes. So this is for directions. So let's now move to curvilinear Newtonian kinetics. So here we have lecture, I assume it's lecture number 9. And dates of today, 6. And for curvilinear Newtonian kinetics, we will start with tangent normal. Okay, so based on the last times, this is the Newton second law. The summation of the force vector will be equal to the mass multiplied by the acceleration vector. So this is the equation that we will be using for this entire chapter. And if we are talking about, or we will be using normal as a tool, I think somebody has his mic on. Can you mute yourself, David? And
my apologies. Yep.
It's okay. Yeah. So the mass multiplied by the acceleration. If we are talking about tangent and normal, so we will be solving our problem in a tangent and normal direction. So this will have two components. The sum of forces in the tangent direction will be the mass multiplied by the A tangential. And the sum of forces in the normal direction will be the mass multiplied by the normal acceleration. And as we know from the particle kinematics, that the A tangent is equal to dv tangent dt, and also this equal to dv tangent ds vt. So we know this from the kinematics, and also we know the normal acceleration is equal to the v tangent square over rho, and if the mass is given as a function y equal f of x, so we know that rho is equal to 1 plus dy dx square, all of these to the power 3.2 over d square y dx square. I believe it's right, yeah. So this is if rho it's not given, but dy equal f of x is given. So here's how you get rho, and then if it's given the tangential velocity, so you square it and divide it by the radius of curvature, so you get the normal acceleration. So this is how to combine between Newtonian kinetics along with the rules that you learn it from the particle kinematics. So let's have a quick example to see how the tangent normal direction works in terms of problems. Let's assume that you are driving on a highway like the I-25, and this highway you will have to take an exit, and this exit or the highway itself is taking a curve like this. And here's your car. And when your car is moving on a straight line, so there's any tangential acceleration, any normal acceleration, so all your velocity is tangent and all your acceleration is tangent. So you can delete tangent because there is no normal acceleration on a straight line. So this is how it works. But if your car is here, so right now you will need let's draw this car like this. Right now you will have to have your tangential acceleration like this, and also you will have to generate a normal accelerations, and this will be translated into forces. So you will be having F tangent equal to mass multiplied by a tangent, and F normal multiplied by equal to mass multiplied by a normal. So the F tangent is developed by the car motor. So your motor is developing a torque, and the torque is like a horsepower, and then the horsepower is transferred into force that pushing the car, so you can have an acceleration in the tangent direction. But the normal direction is generated by the weight of the car. So if your car failed to have a normal component, so if your car failed to have this component, it will shoot in a straight line like this, and you will get out of the curve. So how the car can generate a force in the normal direction, so you cannot get outside of the curve. So let's draw a profile of this road. So here's the profile of this road like this, and your car is somewhere here. Let's assume that this is the car, and here is the tangent direction. Like here is how your car moving. So here's you have F motor is in the tangential direction, and you will have the weight of your car like this, and you will have your car is moving in this direction. So the friction, and this is a dynamic friction, we can call it a kinetic one. So here's you have your weight, and let's put the weight up there. And when you have the weight like this, you will have a normal force from the surface on your car. So this is how the setting of the forces on your car look like. And this will be in the direction I need, like, to move this figure. Okay. And if we, so this is, we call it the free body diagram because it has free body diagram. Free body diagram. And this free body diagram is into the, like, if we have our car like this, so we only captured the tangential direction and the vertical direction z. This diagram didn't capture the normal direction. So if we want to capture the normal direction, so we will have the, if we take a section in this road here, so this curved road will be something like this. Usually all the in the design of the highways, if you are entering a curve, the curve will have a super elevation or an inclination, an angle. So it will be like this, and we will know in a few minutes why this angle is needed. So if your car will be something like this, and let's say this is the driving wheel. So let's see how the axes look like. So if this is the center of mass of the car, and you will have the normal direction is going this way, like this one, and you will have the tangent direction coming outside the plane, like this tangent, and this is normal, and this is the vertical one, and let's call it Z. So let's see how these forces look like. And let's put the forces in this color. So we have the weight is going down, and we have F motor of the car is going in the tangential direction, like outside of the paper, and you will have a normal force coming from the surface on the car. So always the normal force is perpendicular to the surface. So it's something like that, going in this way. So this is the normal force. And we have the friction force. So this car has two types of friction. There's a friction in the direction of the motion. So the car is moving this way. So you have a friction in the opposite direction. And also we might have frictions in this direction, like transversal direction, like this way or this way. So it depends. So if you are like moving on a curve that has with a speed, with a very low speed, like you are almost static, it's not moving, and the radius is very big, like the radius is almost very big, it's almost a straight line. So the car is like on a static and also on a straight line, like the curve is very small. So your car, like if it's a static and you have a slope in the road, so your car might move this way. So a friction will be developed in this way to restrain this movement. Like imagine that you are parking your car on a slope, so your car and will move this way, and this is actually a cross section in the car, not in the on this direction. So we are talking that the car might move this way or this way. So if your car is static, like the velocity is almost zero and the radius is very big, so if the radius is very big, so it's almost a straight line, so the friction will be generated in this way. So what if the velocity is very high? You are entering this curve with a very high velocity and the radius is very, very small. So it's a very sharp curve. So your car might like get outside of the curve like this. Like when you enter the car, it turns out like this wheel is want to go up and your car want like to shift like this, so the friction will be developed in the other direction. So it depends. So the transversal friction depends on how the velocity of your car, the amount of velocity of your car, and also the radius of your curve. That's why whenever you enter a curve on a highway, there is a sign that can reduce your velocity. Like if you are moving here with 75 mile per hour and you enter a curve, you might find the sign is a 45 mile per hour. Why? Because if your velocity is very high and you're entering this curve and it has a certain amount of a slope, it might be the weight of your car will not be able to generate a normal force in the direction of the center of the curvature. So you will not be able to generate this force that can keep you in this curve. So you might shoot outside of the curve. That's why you will have to reduce your speed from 75 mile per hour to 45 mile per hour. So let's see an example how the highway road, the geometric design of the road be like how can we calculate this theta that can make this car stable with a certain velocity and certain radius. So let's have this example. And this is actually an extreme example because this race cars has a very high velocity. That's why the race track has a very, very inclined slope, because the velocity is very high. If we are talking about normal highways, the inclination of this slope might get less because the velocity of the cars is a little less. So let's solve this example. So in this example, it's asking to determine the banking angle, like here is the bank, and sometimes we call it the super elevation angle, theta, for the racetrack, so that the wheels of the racing cars, these wheels, will not have to depend upon friction. So the friction will be zero. So we will not be considered the friction in this way or either this way. So yeah, I would like to mention that mainly the stability of this car to generate a normal force depends on the friction between the wheels of the car and the surface, and also the weight of the car. Not the weight, just like the angle of the super elevation. And the angle of super elevation creates a weight component that can develop this force. And we will see it right now here. So so it says like the angle theta that so that the wheels of the racing cars will not have to depend upon friction to prevent any car from sliding up or sliding down. Assume that the car have a negligible assuming that the car have a negligible size and a mass m and travel around a curve of a radius rho and constant speed. So constant speed, which means that the v tangential is equal constant and the a tangential will be equal to 0. So this is the mean of this piece of information. So let's draw the free body diagram and the kinetic diagram. So here's the car. So let's just draw the free body diagram on this line. So if the car is on this surface, and this surface is inclined with angle theta, we will have the weight of the car is going down, and the normal force will be perpendicular to this surface. So here's n. So if you have this angle equal to theta, so this angle will be equal to theta, this one. And let's draw the kinetic diagram. So this cross section will not show the tangential direction because it's outside of the plane, and we don't need it right now because the A tangent is equal to 0. So we only have the n and also z. And let's assume that the direction of the MA tangent is in this way. So let's solve this problem, and let's first start with the vertical direction. Let's say that sum of Fz equal the mass multiplied by Az. We know that the car is not moving in the z direction, so Az is equal to 0. So let's sum the forces in the z direction. So in the z direction, we will have n cosine theta, which is the component of this one, minus the w, and the w is the mass multiplied by g, and all of these is equal to 0. So the normal force will be equal to mg over cosine theta. So this is the normal force. And let's get the second one, which is the sum of forces in the normal direction will be equal m a normal. And the normal direction, we will only have the component of n in this way. And it's not this way. It should be, we are like if n in this way, we need the one like this, and we got already the one, and this is theta. So this is n cosine theta, and this is n sine theta, and this is the one in the n direction. So let's have n sine theta, and we don't have any other forces, so this will be equal m multiplied by the normal. So we will have a v tangent, let's say v tangent square over the rho, the radius of the curvature of the curve. And we already have n, so we can substitute 1 here. So we will have mg multiplied by sine theta, and we can have cosine theta here, and this will be equal m v tangent square over rho, and we can divide by m, and this is equal to tan theta, so tan theta will be equal to v tangent square over g, multiplied by rho. So this will give us that theta should be equal to tan inverse V tangent square G multiplied by rho. So that turns out that the embankment, the banking elevation or the sober elevation angle theta is a function of the velocity of the car, and the radius of the curve. So it is not a function of the mass of the car. So whatever the mass is, it doesn't depend. That's why it's only a constant velocity on the highway for all the cars. And it's a function of the radius of the curve. So if we are designing a road to be like a race road, and we expecting that these cars will have a high speed like 120 miles per hour, so that means that the theta will increase. And if we also have a very sharp radius, like the radius is very, very small, so theta will be increased as well. So this is actually, and it doesn't actually depend on the acceleration in the tangential direction, because it is not here in this function, and it's also equal to 0 specifically for this problem. Even if it's not equal to 0, it will not be included in this function. So this is how the geometric design of the highway roads look like in terms of the velocities of the car and the radius of the curve, and how we can calculate the super elevation angle, neglecting the friction. If you want to include the friction, you might assume that this car will generate a friction in this direction, and then include it into your equation after you get the one in the tangential direction and the one is in the normal direction, and see how the friction might affect this. But for a factor of safety, we neglect the friction developed by the road, and we only assume that the angle theta will be able to generate a normal force component that can generate a force in the normal direction that can keep the car into the curve. So with this, let's move to another example. Does anybody have any question on this concept? I think if you will be specialized in design of highway roads and civil engineering, you might get in contact with all of these dynamics principles to get the theta, the super elevation of the highway road. So with this, let's move to another example, and let's write it because copy paste takes a lot of time. So it says that we have a 60-pound kid is swinging on, like, here's a swing, and swing has 2 cables like this, and there is a chair here, and there's a kid is swinging on this chair. So you have 2 cables, and if we look from the side view on this swing, it will turn out like this. And it says that the kid started to swing from angle 60 degree. So it starts from here and it's going in this direction. So it's the mass. So yeah, so let's have a discussion here. So it says that the kid has a weight of 60 pounds. So when it's given 60 pounds, so it's a weight. Like if we are talking like the mass of the kid is 10 kilograms, so you will have to find the weight. So this is a mass, and you will have to find the weight, which will be equal to the mass multiplied by g, so 10 multiplied by 9.81. But if we are saying that the weight, when the weight of the kid is 60 pounds, so this is a weight, and if you want to find the mass you will have to divide this weight over g, and this will be 60 divided by 32.2, and the unit of this is a slug. So it's a British unit. I don't know if it's British or not, but this is how is the mass calculated. Yeah, so let's see what is required, and the 60-degree below the horizontal, and if the swing started at rest. So we know it starts here at V naught equal to 0. Find the final speed and the tension in each rod when it gets to this location. So when it moves from 60 degree to 90 degree at this location. So here's C, and here's C dash. Here's the burst and the last position. So right now the A tangential will, normal, actually everything will be changing with theta. As theta is changing, everything will be changing. So let's see how this will happen. And as I told you, you will have to start first with a free body diagram. So let's assume that this is the CAD, and at any angle theta, like let's assume that here's the vertical, and here's the line, and this is any angle theta. So the forces that we have here is the tension force in the cables, and we have two of them, T and T. So we will have 2T here. Sorry. And we have the weight is going down. And the T has an angle theta like this. This is at any random location. And let's draw the, let's make it here. And here's the tangential direction. And here is the normal direction. And let's assume that our M tangent is this direction and M A normal is in this direction. So let's start with the tangential direction. So let's get sum of Ft will be equal to M A tangent. So the forces in the tangent direction, we have this, and it should be this angle will be let's draw it better. So if this is the perpendicular, so this angle should be equal to theta, right? Because this is this and this is equal to 90, and this is equal to 90. So this will be equal to theta. And if we want to the tangent direction, so we will all the tension in the cable is in the normal, so it will not be included, and we will have the weight, which is the 60 pound multiplied by cosine theta, W cosine theta will be equal mass multiplied by A tangent. And the weight is equal to 60 pound, and here's cosine theta, and the mass will be equal 60 over 32.2, because the mass is equal to weight divided by G multiplied by the A tangent. So right now we can get A tangent, and it will be equal to, here is the weight, will be gone with the weight, so it will be G multiplied by cosine theta, which is 32.2 cosine theta. So this is from the tangent direction. So let's get the normal direction. Summation of Fn equal to m multiplied by the normal acceleration. So So we have 2t in the direction of n, and we have negative w sine theta, the component of w, will be equal to the mass, which will be 60 over 32.2 multiplied by v tangent square over the radius. And the radius, I think it's given 10 foot. So it's over 10. So 2t should be equal to 60. Sorry, this is 2t. 60, which is the w, multiplied by sine theta, plus 60 over 32.2 multiplied by the v tangent square over 10. So this is the second equation. So to calculate the tension in the cables, which is required in this problem, we need to find the v tangential, and we know that theta, the tension is needed at theta equal 90 degree. So at this location. So right now we need to find the tangent, the v tangent. So how can we find it? So let's find it from the a tangent. So let's do some calculation here. We know that the a tangent equals 32.2 cosine theta. And we know that the a tangent equals to dv tangent dt and equal to dv tangent ds multiplied by v tangent. So we will be using this one, but we will have to convert it in a form to deal with. So we will have 32.2 cosine theta multiplied by ds, and this will be equal vt dvt. So right now we don't have s, but we have theta. So we will not be able to integrate theta with respect to ds. So we have to transform one of them, either theta to ds or ds to theta. The easiest way is to transform the ds to d theta. So if the swing is moving from here to here, making distance ds is equal to r multiplied by d theta. So ds equal r d theta. So right now we can have 32.2 cosine theta multiplied by r, which is 10, multiplied by d theta, and all of these will be equal to vt dvt. If we integrate this from the position at V node until it gets to the vertical position, we will be able to get the VT. So let's integrate this from theta equals 60 degree to theta equal 90 degree. So because the what is required here, that the swing start here at theta equals 60, and we need to find the tension when it's vertical at theta equal 90. So this is the start and this is the end, and the VT start at rest from 0, and we want to find the VT at the vertical location. So this will give us 322, and if you integrate cosine, so it will give you sine theta, and you will need to do the upper and lower bound, so it will be sine 90 minus sine 60, and this will be equal to half multiplied by vt square, and you will find that the vt of the swing is equal to 9.29 feet per second, and then you will take this from equation 3 and put it in equation 2. So you will find that the 2t will be equal 60 multiplied by sine theta, and we know at this location theta is equal to 90 degree, plus 60 over 32.2 multiplied by VT square 9.29 square over 10, and this will give you that the 2T equal to 76.18 pound. That means that the tension in one cable will be equal to 38.01 pound. So this is what is required. And actually this is interesting, like if you are solving this swing as a static problem and you have a weight here that is equal to 60 pound. So if you are solving it as a static, so the tension here will be 30 and the tension here will be 30. But solving it as a dynamic problem and including the dynamic component will increase the tension in each cable by 8 pounds. And this is because of the normal acceleration generated by your movement on this curve. Like if you have the A tangent is equal to 0, so it will end up with like a static problem. And this is actually the difference between static and dynamic. So this is actually interesting. Does anybody have any question on this problem? Like any of the solutions, any equations that I solved it? Okay, so let's solve another problem, and actually it's kind of similar to the swing problem. So if we, this will take us forever to copy and paste. How about solving this problem in this sheet? Okay, so in this problem, it says that we have a 60-kilogram skateboarder in this figure, coasts down the circular track. If he starts from rest at theta equals 0, like starting at rest from this point, determine the magnitude of the normal reaction of the track that exerts on him when theta equal to 60. Like when he comes here, he needs to find the amount of the normal force here. So let's solve this problem. So let's first like assume that this guy at any random angle theta here and nothing is mentioned about the friction, so we will not be dealing with friction in this problem. However, he is exposed to friction, but once it's not mentioned, so we will not be included it in our analysis. So let's now see what is the forces that we have on this skateboarder. So he will have the weight going down, and we know that he's moving on a surface. This surface is something like this, and this surface should be, the normal reaction should be normal to this surface, so we will be having a normal force like this. And if this is theta, so this angle will be theta as well, and this angle will be theta as well. And so this is for the free body diagram. Let's draw the kinetic diagram. So let's assume that these are the direction of the tangent, and these are the direction of the normal, and we have MA tangent in this direction and MA normal in this direction. So we have the mass equal to 60 kilogram. So we can get the weight will be equal to mass multiplied by G. So it's 60 multiplied by 9.81. And so it will be 588.6 Newton. So let's solve in the tangential direction. So the summation of the F tangent will be equal M A tangent. So in the tangent direction, we will have, like in this direction, the normal of the surface is in the direction of the n, and we will have the component of W in the positive direction. So we'll have W cosine theta, and this will be equal to M A tangent, similar to the last problem. So we will be having the mass multiplied by G equal to cosine theta, and here is MAT. So we can cancel the m's, so the A tangential will be equal 9.81, which is the G cosine theta. So we have A tangent as a function of cosine theta. And let's get the in the normal direction, which will be equal MAN. And in the normal direction, we have the normal force from the surface in the positive direction. So we'll have N, and we have negative W sine theta equal to M multiplied by V tangent square over R, which is 4 meters. So we don't know N, which is, this is what is required in the problem. And here we have W 588.6 equal M, which is 60, multiplied by VT square over 4. So N is equal to 588.6 plus 60 multiplied by V tangent square over 4. So we need to find the V tangent so we can calculate N. And we will not be able to do this until we deal with the A tangent. So from this equation, let's say this is 1. From 1, A tangent equal to 9.81 cosine theta, and this is equal to dV tangent ds applied by VT. And we know from last time that the ds is equal to r d theta, and we have r is equal to 4. So right now we will have 9.81 cosine theta multiplied by 4 d theta will be equal to Vt dVt. So let's integrate here. So the integration will be from theta equal to 0, because it listed in the problem, it starts from rest at, so the V node is equal to 0 at theta equals 0. and he needs at theta equals 60 degrees. So let's put the upper limit theta equals 60, and we know it started with v tangent equal to 0 up to vt, which is required. So this will give us 4 multiplied by 9.81, so it will be 39.24. And the integration will give us sine theta, and we will have to integrate with the upper limit minus the lower limit, sine 0. And here will be half multiplied by vt squared, and then we will be able to get the v tangent, which will be 8.24 meter per second. So we got the v tangent. So right now we can solve this problem, this equation, sorry. So from 2, n will be equal to 588.6 plus 60 multiplied by 8.24 square over 4, and this will give us 1.53 Newton. So this is the normal force on the skateboarder when he get to angle 60. And if it asks for a different angle, like theta is equal 30, so it will be the same with everything, and we will keep the a tangent as a function of theta, and then we will integrate this function from theta equals 0 to theta equals 30. We do this because the acceleration is keep changing with theta. Like when theta is equal to 0, so cosine 0, so it will be 9.81. So the tangent direction will be 9.81. But when he comes here, the a tangent will be different, and here the a tangent will be different. And actually the velocity will be different. That's why we keep it as a function of theta, and then we use the kinematic form, this one, to account for the v tangent from the a tangent. So this is actually how it works. You basically, it's only 2 equations, this one and this one. And the others is that we are using our background in the kinematics of the particle. We have like another 5 minutes. I would like to does anybody have any question on this problem? Any issues?
I have a quick question.
Yeah, go ahead.
So when you integrated the acceleration component, I'm not really sure where the format of that integration came from.
Okay, this one?
Yes, the form 1.
Okay, so let's have it. So are you okay with the a tangent is equal to 9.81 multiplied by cosine theta?
Yes.
Okay, so a tangent, the tangential velocity is the time rate of a change of the tangential acceleration is the time rate of the tangential velocity. So it's dv by dt. And from the chain rule, we have dvt, and we can put the s here and the s here, and we have dt here, like you put with the chain rule. So you can have ds and ds at this location. So if you take them together, it will end up with dv dt, like this one. So ds dt is the time rate of a change of the position, which is the vt itself. So the a tangent is equal to dvt ds multiplied by vt. And this is what we know, et ds dv dt So this is one of the equations that we learned in the kinematics of particles. The acceleration multiplied by ds will be equal vt dv dt. And what we did is that we got the ds because it's a curvilinear motion, so the ds can be a function of d theta. So here is ds, and this is r, and ds is equal to r multiplied by d theta. So this is how we got ds, and then we have a tangent as a function of cosine theta, so 9.81 cosine theta multiplied by ds, which is the r multiplied by d theta. So r will be 4 d theta, and all of these will be equal to vt dv dt.
Okay.
And what we did is that we get the integration from theta equal to 0, where the skateboarder start up to theta equals 60, and from vt equals 0 because it starts at rest, until the velocity that we are looking for. Then the integration of the cosine is sine, and then you multiply these, and then the integration of the vt will be half vt squared. Did you get it?
Yes, that is very helpful.
Okay. Does anybody have any other question? If anybody have any question, like want to explain any basics, maybe I skipped some basics, like anything is what is coming from. So you might ask this question. All right. Okay, so I just like want to bring your attention to something, like how about if we, okay, so I think when we, at some point we constructed the kinetic diagram and said, like, if this body is moving, a skier is moving on this surface, and we said that this is the direction of x-axis and this is the direction of y-axis, and we know for sure that this skateboarder is moving in this way. So this is the direction of the velocity, and this is also the direction of the acceleration. So if you got the velocity, it will be negative. And if you got the acceleration, it will be also negative. So the negative acceleration is not meaning that this body is decelerating. However, we learned it from before, if a body have a negative acceleration, it means that the body is decelerating. But actually, you will have to look on the direction of the velocity. If the velocity in this direction and the acceleration in this direction, so that means that the velocity is increasing, but it's increasing in the negative direction. If the acceleration is positive, that means, like, let's assume that this is v, and this is a is positive. Here, however, a is positive, but the body is decelerating because it is going in the opposite direction. So if you want to know for sure if the body is decelerating or accelerating, you will have to look on the sign of v and the sign of a, and you multiply them together. If it gives you a positive value, so it means it's accelerating. If it gives you a negative value, it means decelerating. And let's test this. So if the velocity is negative and the acceleration is negative, so you multiply negative by negative, it will give you positive. That means that the velocity is accelerating, but in the negative direction. If one of them is positive, like let's assume that the acceleration is positive, but the velocity is negative. So if you multiply negative by positive, it will give you a negative. That means that the velocity is in direction and the acceleration is in different direction. So it will be negative. So I just like want to make this point very clear. Sometimes when you are given its a negative value, you assume it's that it's a decelerating body, but you will have to look where is the direction of the velocity. Does anybody have any question on this principle? All right, so that's all for now, and I hope that you will be prepared for tomorrow's quiz, and we will have our first 30-minute to continue with curvilinear kinetics with the application on the polar coordinate system. and see you guys tomorrow. Actually, we have a help session at 1. So if you have any questions in the homeworks or related to the quiz, you just log in into the Zoom meeting and ask your questions. See you guys tomorrow.
Thank you very much, Professor.
Thank you. Have a good one.
See you tomorrow.
See you.
So you said tomorrow, Omar, at 1, there's the help session?
No, today.
Today?
Yeah, I sent it in the announcement. So you will have the link in the home.
Okay.
And I will send it in the announcement in a few minutes from now.
Okay, cool. Thank you. Yeah, I'll see if I can make it. I'm gonna keep looking through my notes and see how the quiz goes tomorrow, and then I just want to go from there. I just feel like I don't know why I understand it, and then once I see the problems myself, I just get confused.
Okay, yeah, just like I think you will be the only one in the live session. So if you have any question, we can spend the whole hour together.
Okay, cool. Thank
That's
you
good.
so much, Omar. Appreciate it.
Have a good one.